Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson about Argand diagrams and the polar representation of complex numbers. In the last lesson, we learned about the multiplication and division of complex numbers. Today, we will study the Argand plane. We will also learn to represent any given complex number in a polar form. Are you ready, students? Let's get started. The Argand plane is another name for a complex plane or Z-plane. The complex plane is a geometric representation of the set of complex numbers. It is established by the real axis and the imaginary axis. We can think of it as a modified Cartesian plane. The real part of a complex number is represented along the x-axis, and the imaginary part is represented along the y-axis. Complex planes allow us to make a geometric interpretation of complex numbers. Under addition, they add like vectors. This is a reflection of a complex number. If z equals x plus y iota, then its reflection equals x minus y iota. The 2 points have the same value for the real axis and opposite values for the imaginary axis. You see, students, we may establish a one-to-one correspondence between the set of complex number and the set of points on a plane. Since we are expressing complex numbers as vectors, there are several ways in which we may manipulate them. Observe this complex plane. Z1 and Z2 are two complex numbers which have been expressed through vectors. The modulus of Z1, represented this way, is the length of the vector representing the complex number Z2. Z1, or the distance from the origin to the point corresponding to Z in the complex plane. The difference between the moduli of Z1 and Z2 is expressed this way. It is the distance between points Z1 and Z2. We can add complex numbers as we would vectors by using parallelogram law. The multiplication of two complex numbers can be expressed as polar coordinates. The magnitude, or modulus, is the product of the two absolute values. The angle, or argument, of the product is the sum of the two angles. Let us try making a complex plane, students. Select a partner. Then draw a complex plane and graph these 4 points. Please identify the quadrant in which each complex number belongs.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. The first complex number is represented with a vector with end point 2, 1 in the first quadrant. The second complex number is represented with a vector with end point 2, -6 in the fourth quadrant. The third complex number is represented with a vector with end point 6, 4 in the first quadrant. The fourth complex number is represented with a vector with end point -1, -2 in the third quadrant. Good work, everyone. Since complex numbers can be expressed as points on a plane, we can use polar coordinates rather than Cartesian coordinates. We will define the non-zero complex number z is equal to x plus y iota. The modulus of z expressed as r is equal to the square root of the sum of the squares of x and y. Theta is the angle made by the vector corresponding to z with the positive x-axis. X equals r times the cosine of the angle. Y equals r times the sine of the angle. Therefore, we can conclude that z equal to the sum of r times the cosine of the angle and iota r times the sine of the angle. This may also be expressed as r times the sum of the cosine of the angle and iota times the sine of the angle. This is called the polar representation of z. When a complex number is written in the form of z equals r times the sum of the cosine of theta and iota times the sine of theta, theta is called an argument of z. The particular argument of z that is greater than -pi and less than or equal to pi is called the principal argument of z. The principal argument of 1 is 0. The principal argument of -1 is pi. The principal argument of iota is pi over 2. The principal argument of negative iota is -pi over 2. Note that y over x equals the tangent of theta if x does not equal 0. So theta is determined by this equation up to a multiple of pi. Theta is equal to the inverse tangent of y over x plus k times pi when k equals 0 if x is positive, k equals 1 where x is negative and y positive, k equals -1 if x and y are both negative. We have time for one more activity, everyone. Please demonstrate what you have learned by expressing this complex number in polar form.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again. Here is the formula for a polar representation. We have also learned that the principal argument of iota is pi over 2. Therefore, we can substitute the appropriate values to find our answer. Here is the polar form of 3 iota. If that was your answer, great work. Are you ready for one more activity? Please determine the polar form of the equation 1 minus the square root of 3 iota.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Let us look at your answers, students. First, we must calculate r by using the formula r equals to the square root of x squared plus y squared. In this case, our x value is 1 and our y value is the square root of 3. By using these values, we find that r is equal to 2. We use our polar representation equation and enter our values. Sine theta equals y over r, since theta is on the 4th quadrant. This means that sine theta equals the negative square root of 3 over 2, which is 300 degrees. Measured along the anti-clockwise, theta equals 5 pi over 3. Therefore, z equals r times cosine theta plus iota times sine theta. Substituting the proper values, we find that z equals 2 times cosine 5 pi over 3 plus iota times sine 5 pi over 3. If you manage to solve this problem, you have done an excellent job. That is all for this unit, students. We have learned a great deal about complex numbers. I will see you in the next unit. Thank you, teacher. Thank you, students.